Why is carbon fiber ridiculously strong and still expensive enough to feel like it's made of money? Because carbon fiber isn't a material the way steel is. It's a system, millions of hair-thin carbon strands arranged in specific directions, then locked together with resin. Done right, it's like taking a bundle of tiny cables and turning them into one stiff, lightweight beam, perfect for aircraft parts, race cars, and high-end bikes. It starts in a place that doesn't feel futuristic at all, giant spools of precursor fiber. Think of it like plastic thread, except it's engineered to become carbon later. Thousands of filaments move together as a tow, sliding through rollers in long, controlled production lines. Then comes the transformation step. The precursor goes through industrial heat treatment stages where the chemistry changes and the fiber becomes carbon-rich. At a microscopic level, you're stripping away a lot of non-carbon atoms and leaving behind a structure that's much more carbon-dense. That's where carbon fiber gets its reputation, but also where cost starts climbing, because this is specialized, tightly controlled industrial work. After that, the fiber surface is treated so resin can actually bond to it. Without this, your super material can fail in a boring way, layers separate, cracks run, and strength disappears. Manufacturers often add a thin protective coating, called sizing, to keep the fibers from getting damaged and to help processing downstream. Now the fibers can be turned into different forms. Some are woven into fabrics, like that iconic checker pattern. Others are kept as unidirectional sheets where all fibers run the same way. That second one looks plain, but it's a beast when you load it in the direction of the fibers. Here's the key idea most people miss. Carbon fiber by itself is not the whole story. The resin matters. Fibers are like rebar. Resin is like concrete. Rebar without concrete is just a bundle of rods. Concrete without rebar is brittle. Put them together and you get a structure that shares load, resists cracks, and holds shape. Now we enter the craft part, layup. A mold defines the final shape. Technicians place layers, called plies, onto that mold. But the magic isn't more layers. It's direction. One layer might run along the length of the part for bending strength. Another might run across it for stiffness. Others might be angled to fight twisting. That's why carbon fiber can feel smart. It can be engineered to be strong exactly where it needs to be, and not waste weight where it doesn't. Next comes vacuum bagging, which is basically quality control before curing even begins. The part is sealed under a flexible bag, and air is drawn out. Removing trapped air matters because air becomes voids, and voids become weak points. Vacuum also compresses the layers together so the resin spreads evenly and the fibers pack tightly. This is the difference between a clean laminate and a disappointing one. Then curing, the moment the material locks in. In an industrial curing chamber, the resin changes from a workable state into a solid network that grips the fibers and transfers load between them. Think of it like setting cement, except this is engineered chemistry designed for predictable strength. When it's done, the part holds its final shape, stiffness, and performance. After curing, parts are demolded, trimmed, and inspected, often with non-destructive methods, because tiny defects can matter in high-performance structures. So here's my question for you. Why do you think carbon fiber shows up more in aircraft and racing than in everyday cars, performance, cost, or repairability?